Okay. Welcome everyone. I think I've got this thing going now. So this is what we're going to cover in the second half. We're going to explain the first and second laws of thermodynamics. We're going to address again why there's no away when we throw things away. We're going to talk about photosynthesis and respiration. Um, the qualities of water and why they're essential for life. And then we're going to talk about the cycles for carbon, nitrogen, phosphate, sulfur, etc. So we're going to start with energy. And what is energy? Energy is the ability to do work. Okay, so if you want to move something, if you want to heat something, uh, energy is required. There's a lot of different types of energy: heat, light, electrical, chemical, um, electromagnetic. There's a long list for the ways that energy can be formed or translated. Okay. Um, a- Another way of addressing energy is kinetic energy. By definition, kinetic energy is energy in movement. So if something is moving, that is kinetic. Um, they're showing a little bit of water coming off of here, off of this fall. The water is moving down, that's kinetic energy. The water is on the top that's not moving, but is ready to fall down. That's potential energy. So another word for potential energy is stored energy. So water can be kinetic, a rock can be kinetic, a car can be kinetic. Uh, when we move around, we are expending kinetic energy. We're using potential energy stored in lipids and in sugars and even proteins in order to move around and carry out kinetic energy. So potential energy again is stored energy. If you have if you park a Volkswagen at the top of a hill and you put the brake on, that's potential energy because when you take the brake off, it's going to come back down. Okay. Chemical energy. So this can be a battery. If you have a battery and that battery still has the ability to produce energy, that is stored energy. That is potential energy. The carbon bonds in the food that we eat, and the sugars, the lipids, and the proteins, that's potential energy. Okay. When we put fuel, gasoline in our car, that gasoline has potential energy stored in its molecules. As a matter of fact, the parallel between respiration and combustion are they're almost identical, including the efficiency. The efficiency of a car and the efficiency of the human body is almost identical. It's around 18 to 20%. And the reason for that is because we're both consuming potential energy. We're both catabolizing that energy in order to extract it and turn it into kinetic energy. So we say that metabolism can be seen as a process of converting. That's beautiful. Metabolism can be seen as a process of converting potential energy in lipids, carbohydrates, and proteins into kinetic energy, the energy of movement. Okay. Let's see. The reason that we are inefficient is because the majority of the heat, the majority of the energy that we harvest leaves our body in the form of heat. And we've talked about this before, but heat is necessary in order to drive chemical reactions. We're 3 trillion chemical reactions every few seconds, and if those chemical reactions are going to take place, they have to be in a dynamic environment, in a good in a good solvent, which is water, and the molecules have to be diffusing and have the ability to find each other readily and quickly, because our bodies are demanding, because we are demanding, and these the reactants to these chemical reactions are going to find themselves quickly enough. The only way that that can happen is by having our bodies be hot, so that this diffusion can take place quickly. This has been measured in advanced laboratories. We know that, for example, if you're to put a bioluminescent, not a bioluminescent, but a fluorescent tag on the surface of a cell, that tag would circumvent the surface of that cell in approximately 3 seconds. So you can imagine what's happening inside that cell. Molecules are moving so quickly in order to find them and facilitating these chemical reactions. And the reason that they're moving quickly is because we are using this heat to drive these reactions as quickly as possible. So the first law of thermodynamics states that energy is conserved. In other words, energy is neither created nor destroyed. There's no such thing as perpetual motion. Why do we care? Uh, we we have to continue to harvest energy as living organisms, and the energy that we give off afterwards is not as good a quality as the energy that we received. That's true of the entire trophic level. Um, so you have these beautiful plants. Plants are so important to us because they harvest the sun's energy, and then they use water, carbon dioxide, and and they form sugar from it. They store, so they turn the electromagnetic radiation of the sun, and they store it into potential chemical energy in sugar. Okay, and that potential energy, well, is not as, it doesn't have as much energy as the energy that the plant first received from the sun. Okay, and when we consume it, the amount of energy that we're going to extract is also going to become less, because we're going to dissipate that energy, but it's going to be of a different quality. And so as energy goes through transitions, you end up with the same amount of energy, but it ends up being dispersed at each stage. The second law of thermodynamics states that with each successive energy transfer or transformation in a system, less energy is available to do work. Okay, so again, it comes to the fact that you and I are only about 20% efficient. The other 80% of the energy is dissipated to the universe. And the second law recognizes that disorder or entropy tends to increase in all natural systems. Okay, so you have to think to yourself, if entropy or chaos is the law of the universe, then why are our bodies not chaotic? And the reason for that is because the second law tells us that we can maintain order. We can fight entropy. But in order to do that, we have to invest energy, right? So let me give you a for instance. You're babysitting a couple kids, you put them in a room, you go, hey, I've got something to take care of. I'll be back in 10 minutes. You close the door and you walk away. And then 10 minutes later, you come back and you're like, oh my goodness, what has happened here? The toys are all over the place. The Cheerios are on the curtains. The milk is thrown all over the place. It's a disaster. Okay. Um, we can get upset at them, but honestly, all they're doing is following the second law, where it says that the disorder in the universe is going to increase. Okay. So that's it. We're done. The room is going to stay that way, right? No. You bring them in, you make them put all the toys back into the toy box. You bring the vacuum cleaner, you bring the mop, you bring you bring the towels, you clean everything up, and a few moments later, the room is clean again. So we're violating the second law of thermodynamics? No, we're not. We created order from disorder, but in order to do that, we had to put effort into it. We had to invest energy. Okay. That's the reason that you and I have to be eating all the time, because we have to continue to consume energy in order to maintain our biological system. Okay. So if we cannot, I love this thing. Sometimes it fits, sometimes it doesn't fit. There we go. So if we want to maintain our life, our order in our bodies, we have to continue to consume energy in order to maintain that order. And if you don't recognize that we're order, think about the fact that in the hierarchy of life, you have, you know, organelles that are organized into cells. Cells are organized into tissues. Tissues are organized into organs. Organs are organized into organ systems, and then organ systems are organized into organisms. So we are nothing but pockets of organization. Okay. For nearly all life on Earth, the sun is the ultimate energy source. We say this because it came as a surprise to us not too long ago that this is not universally true. Okay. This energy is captured by green plants, which are often called primary producers because they create carbohydrates and other compounds using just sunlight, air, and water. So again, this is very, very important. But there are organisms that get energy in other ways. These organisms get their energy from chemosynthesis. This is important. You should remember this. A process which allows them to extract energy from inorganic chemical compounds such as hydrogen sulfide deep in the Earth's crust or deep in the ocean floor and in hot springs such as in Yellowstone National Park. We can find extremophiles. Extremophiles are bacteria that love extremes, that gain their energy from chemosynthesis or extracting energy from inorganic chemical compounds such as hydrogen sulfide. This came as a surprise to us because, you know, we revisited the Galapagos Islands, and we had a little maneuverable submarine, and we went down to the volcanic vents. The volcanic vents, as the name implies, are vents made out of magma that are incredibly hot. I mean, they can melt steel. So, what are we expecting to find down there? Maybe a lot of things. What we did not expect to find was life. And surprisingly, that's exactly what we found. So here we are, hundreds of meters below the surface of the ocean, in a volcanic vent that melts steel. And here's this very healthy ecosystem. There's tube worms, there's uh, um, there's crabs, there's shrimp. I mean, all these organisms very happy. And so that blew our mind away. Why? Because up until then, every biology book in our world said that the sun was the ultimate energy source. Here we're finding these organisms at the base of the ocean that have absolutely nothing to do with the sun, and they have a very vibrant ecosystem. So we have to realize that what they were doing is they were getting their energy from hydrogen sulfide through chemosynthesis. So they were harvesting their energy from different high energy metabolites. Very, very incredible. This is what it looks like. These are tube worms. Some of these are clams. I mean, they look pretty healthy, pretty happy. But for the rest of us, we have to depend on these beautiful green plants, okay? What do we have? We have a beautiful star. That star gives us light in the yellow spectrum, okay? And we have plants that harvest that energy through photosynthesis. And photosynthesis converts light into useful chemical energy into bonds that hold together organic molecules, specifically sugar. Okay, so here's a visible spectrum, and plants absorb light preferentially in the red and the blue, and they reflect in the green. That's why plants are green in color, because they are accepting everything else except that part of the visible spectrum. Let's see here. A lot of information here, but here's where the meat is at, okay? The glucose, here it is. The glucose produced by photosynthesis is an energy-rich molecule that fuels all metabolic processes of cells. The energy in this chemical bond can be released in a process called cellular respiration. So this is cellular respiration. So if we're to take this equation and turn it around, we would have photosynthesis, okay? So cellular respiration, that's what you and I are doing right now to stay alive, okay? This is taking place in the cytosol and the mitochondria of your cells. We're gonna cover this. We're not gonna cover this. We're gonna cover this in biology. But what do? We have sugar, okay? We breathe, so we take oxygen in. We extract energy. That energy is adenosine triphosphate, the currency of energy in our cells. About, depending on who you want to believe, between 15 and 18 molecules of adenosine triphosphate, which is beautiful. And then we release what? How do you test to see that somebody's not a vampire? How do you know that you're not a vampire? You take a mirror, and if you can see yourself, you're not a vampire. No. That's not what I meant at all. You take a mirror and you breathe on it. And if your breath condenses, that means that you're breathing water out and you're alive. And you're not a vampire. Okay? So we're breathing out water and we're breathing out carbon dioxide. Is that cool? So this is cellular respiration. We take sugar, we use oxygen, we breathe out water vapor and carbon dioxide, and we release about, I said 18, but I was wrong. It's around 32 molecules of adenosine triphosphate. And that's the energy that we get. Sound incredible? Now take this beautiful equation and turn it around. We take energy. What kind of energy? Energy from the sun, light energy. And then the plant takes that light energy, it takes carbon dioxide, our waste, water, and it produces oxygen for us, and then it produces sugar for us. How can you not love plants? How can you not love them? They're taking energy from the sun, they're taking stuff that you and I are trying to get rid of, a little bit of water, and they give us oxygen and energy. So this way is cellular respiration, and in the opposite way is photosynthesis. Okay, so what does it take to make sugar? To make sugar, it takes water, carbon dioxide, and energy, light energy. It's a beautiful thing. It's a beautiful thing. Okay. If you're a car, you take gasoline, you take oxygen, You release energy in the form of heat, and then you release water and carbon dioxide. So we and cars are doing the exact same thing. We're carrying out cellular respiration. Now, here's another thing that I'd love to cover because amusingly, a lot of people don't know. For example, if you ask somebody, do plants carry out photosynthesis? Well, of course, everybody knows that plants carry out photosynthesis. Okay, do plants carry out cellular respiration? I don't know. Yeah, they do. Okay, you see, plants are carrying out photosynthesis to produce sugar. Do you know who that sugar is for? It's not supposed to be us. It's supposed to be them. They're making energy for a rainy day. And by rainy day, I mean it doesn't rain. And when you have that rainy day, okay, then they take these sugars that they have accumulated and they carry out cellular respiration and they make the energy necessary for them to grow. So we're kind of mean, aren't we? We grow these delicious little carrots and beets and peas and everything. And instead of having the plant have the sugar, we're like, you know what? We're going to have the sugar. Thank you. But that's what we do. We grow plants specifically for this. But the point here is that plants carry out photosynthesis to store potential energy in the form of sugar. But then when they need to grow or divide or do anything that requires energy, they carry out cellular respiration in order to have the energy to do it. Is that cool? Okay. Let's keep on going through here. Okay, the cycles. Okay. They're called biogeochemical cycles. Why are we studying them? Because they deal with the elements that we care about. We're going to start with the most important one, the hydrologic cycle, water. Okay. The path of water through our environment is perhaps the most familiar biogeochemical cycle. Most of the Earth's water is stored in the oceans, but solar energy continually evaporates this water and winds distribute water vapor around the globe. Water condenses over land surfaces in the form of rain, snow, or fog, supporting terrestrial ecosystems. Organisms emit the moisture they have consumed through respiration and perspiration. Eventually, this moisture re-enters the atmosphere or enters lakes and streams, which ultimately return it to the ocean. So there you have it. And look at this little detail right here. So we have approximately 425,000. I want you to grasp what this is telling you. Cubic kilometers. What is a cubic kilometer? A cubic kilometer is the volume of a box 1 kilometer long, 1 kilometer wide, and 1 kilometer high. That's 1 cubic kilometer. So how much water is coming from the ocean? 425,000 cubic kilometers. Okay, so this is an incredible amount. Of that, the majority precipitates back into the ocean, but a great amount of it, 40,000 cubic kilometers, precipitate over mountain ranges of snow or the valleys to provide water. Okay, the water here, of course, percolates through the rock, and it fills up caverns and artesian wells, and that flows under the ground back out to the oceans slowly. Okay, switching to the second one, the carbon cycle. So the carbon cycle begins with photosynthetic organisms taking up carbon dioxide. This is called carbon fixation. Very important, because in case you're not keeping track of current events, the biggest hiccup right now is global warming, which is carbon dioxide and methane. Okay, and anything that can allow us to fixate carbon, in other words, turn it from carbon dioxide to a solid, is desirable. And who does this? Plants and algae, okay? So this is called carbon fixation because carbon is changed from a gaseous carbon dioxide to an organic molecule like sugar. The sugar molecule is absorbed into the bloodstream of animals where it is made available to the cells of cellular respiration or the production of more complex biomolecules. If it is used in respiration, it may be exhaled as carbon dioxide again in an hour or less, and a plant could take up that exhaled carbon dioxide the same afternoon. So these are things that literally happen day to day. Let's see, the carbon atoms from the sugar molecules can remain a part of the body until it decays after death. Okay, so let's take a look at this. So there's carbon coming from the soil, and we got to measure. Now it's not a volume; it's a weight. So, what's a ton? We usually talk about metric tons. So it's 1,000 kilograms, or about 2,200 pounds. That's a ton. Now we're dealing with gigatons. What's a gigaton? Well, you can have a kiloton. Kilo is 1,000. You can have a megaton. That's 1,000,000. Or you can have a gigaton. That's 1,000,000,000. So 1 gigaton is 1 billion tons. What are we talking about? 100 billion tons. Holy moly, that's a lot. So this is carbon dioxide coming from respiration up into the atmosphere. Okay. Photosynthesis recaptures about the same amount, 100 gigatons by plants. So this is an equilibrium. We're doing okay. All right. Look at the let's look at the ocean. The ocean is considered a carbon sink because it takes carbon, and then that carbon gets incorporated into organic sediment and ends up in marine plankton, and then those seashells come together and they're pressed at the bottom of the ocean. So that's a carbon sink that lasts for a very, very long time. So when you go to Home Depot and you're having your kitchen remodeled, you have that beautiful granite slab that they're going to put on there. This is where it came from. It's quarries of fossilized phytoplankton that captured carbon from our world a long time ago. And these things will look beautiful in your kitchen all day, every day, unless you use hydrochloric acid, because hydrochloric acid will burn through it like nobody's business. So don't use any hydrochloric acid on your kitchen. But take a look at it. Atmospheric carbon dioxide, 92 gigatons, biological processes. So there's your carbon sink, okay? And then coming back is about 91 gigatons. In other words, the oceans, incredibly, are still functioning as a carbon sink, meaning that they are not releasing as much as they're absorbing. They're releasing a lot, but not all of it. So they're still functioning as a carbon sink. So you have to look at it. If ecosystems are in balance and the oceans are functioning as a proper carbon sink, then who's to blame? Us. Of course it's us. It's always us. Here's us burning fossil fuels the way that we keep on being told not to. And as a consequence of burning fossil fuels, we're creating about a net 7 gigaton movement per year of carbon dioxide. That's ridiculous. That's ridiculous. The nitrogen cycle, okay? So plants acquire nitrogen from nitrogen-fixing bacteria. This is very interesting because this is one of the few cycles that require bacteria. that live in and around their roots. These bacteria combine gaseous nitrogen with hydrogen to make ammonia and ammonium. Other bacteria then combine ammonia with oxygen to form nitrites. A third group of bacteria converts nitrites to nitrates, which green plants can absorb and use. Okay, so this is incredible stuff. Okay, it really is. Contemplate. Nobody cares anymore because you can just go to the local fertilizer store and buy fertilizer of, nitrogen, phosphorus, and sulfur. But I'm going to tell you, it's not a good thing. The way we used to do it when we were smart is that farmers would grow plants, legumes. They would grow legumes in their fields because these legumes had nodules that attracted nitrifying bacteria to their roots. Okay. Now, this is incredible. Okay. Imagine that you're in the desert, you're dying of thirst, and next to you, there's a 55-gallon drum of delicious cold water. And the problem is that you cannot open the drum. Would that be frustrating? Because I got to tell you, that's exactly what happens to us. Okay. One of the most important nutrients for plants and for animals is nitrogen. A lot of times we can't grow plants because there's absolutely no nitrogen in the soil, right? And if you're asking, so what? Well, the so what is that the air that you're breathing right now is not primary oxygen. So in fact, the air you're breathing right now is only 18% oxygen. It is 80 to 82% nitrogen. So imagine you're a plant on the ground and you're not living because you don't have nitrogen, and the entire atmosphere around you is rich in nitrogen and you can't get to it. Frustrating, right? How do we fix this? The answer is nitrogen fixing bacteria. So what you do is you plant legumes. These legumes have evolved to attract nitrogen fixing bacteria to root nodules. Okay. These bacteria remain in the root nodules. They take nitrogen from the atmosphere and they fix it into ammonia, ammonium, and then nitrates that the plant can finally use to make amino acids. Okay. Pretty cool. Now what do? Here's a weird part. You till the plant into the soil. You don't harvest it. You till the plant into the soil because you have just made a plant that's a rich source of nitrogen. Now you take the crop that you care about and you plant it, and it's going to do great because you planted a legume before you grew that product. Now, the reason this is better than anything that we do right now is because now we just throw nitrogen all over we throw ammonia all over the ground. That is uncontrolled. It can go into streams, it can go into rivers, it can go into ponds. And because it's uncontrolled, it's called eutrophication. Eu is supposed to be true or good. Troph means to eat. So eutrophication would imply good eating, right? No, that's not true. It's actually an excess of nutrients that brings about algal growth. And then when this algae grows in these rivers, or more importantly in lakes, it sucks all the oxygen from the lake in the local zooplankton and fish and everything that lives in that lake ends up dying because of it. And that's because we choose to fertilize more than we should. So we're causing a catastrophe because we choose to use methods that are not necessarily sound. You can see right here, your author put in this diagram, fertilizer runoff. That's called eutrophication, okay? So that's excess nutrients, and this is what's going to give rise to algal growth in the future. So again, nitrogen comes in from bacteria, okay? That nitrogen gets captured into ammonia and ammonium, and then finally to nitrates. Once it turns into nitrates, plants can use it. Then secondary consumers, deers, us, eat those plants, and we become part of the cycle. When we die, the nitrogen comes back into the ground, okay? But here's us causing a problem, okay? And the problem is improper or excess use of nitrogen, okay? Look at that, isn't that beautiful? So these are nitrogen molecules are converted to usable forms in bumps or nodules on the roots of this bean plant. These nodules are massive root tissue containing many bacteria that help convert nitrogen in the soil to a form that the bean plant can assimilate and use to manufacture amino acids. Beautiful. Okay, I think this is the last. Oh, okay, we're almost done. So we have phosphorus and sulfur. Now, phosphorus, if you forgot where that's coming, we need that for DNA, and we need that for energy molecules such as GTP and ATP. So phosphorus is a very important element, okay? And one of the things that's interesting about the phosphorus cycle is that there's no atmospheric component to it, okay? So phosphorus is very much something that comes from sources of minerals, and then primary decomposers can break apart some of those phosphates, and then eventually that gets introduced into primary consumers and secondary consumers later on. We are the problem. We love to add too much phosphate and cause eutrophication, okay? But an essential element, and again, no atmospheric component to this. Sulfur, do you guys remember why sulfur is important? We have 20 amino acids, and exactly one of them, cysteine, uses sulfur. And believe it or not, very, very important. So most of your sulfur is tied up underground in rocks and minerals. Weathering emissions from deep seafloor vents or volcanic eruptions release this inorganic sulfur into the air and water. Living organisms, especially bacteria, also sequester sulfur, and biogenic deposits are released into the environment. This is interesting. We have done this to Europe for a long time, but when we burn coal, one of the things that coal is rich in is sulfates, and these sulfates associated with the water in the atmosphere, they literally make sulfuric acid. So as we have undergone the industrial revolution here in the United States, and we've run everything on coal power for over 100 years, we have literally been raining sulfuric acid on Europe. I wouldn't be very happy with this if I was them. But there is a bacterial component to it. Okay, but again, it's it does run through the atmosphere, and it's something that is an essential nutrient. It's required, but the amounts of it that are necessary are kind of low. So this is not something that causes eutrophication in the world. Um, Now, another source of sulfuric acid is volcanoes. The reason that this is important is because if there's too much sulfur in the atmosphere, it will literally reflect the sun's rays. So we actually have a year in our American history that we call the year without a summer. And what we had is we had a volcanic eruption on the other side of the earth that released a lot of sulfates, made a lot of sulfuric acid in the atmosphere. It reflected a lot of the sun's rays, and it cooled the temperature of the earth. So these are significant problems, but they're not anthropological. There's nothing that you and I can do about them. So that brings us to a conclusion. I hope I didn't bore you guys too much. I'm making a sincere effort to only cover the most significant aspects of this. So until later, it's been fun talking to you. Thank you.